In this example, we will do an axisymmetric problem in EMWorks 2D from scratch. Okay, to start with, let us first create our model, basically our surfaces in EMWorks 2D. So I would just like to create some center lines which will help me to orient my model. The first thing that I want to create is a rectangle. This is a rectangle that is going to represent the core when you revolve it. So we'll see that a little later once the model is completed. So let us quickly dimension. So we want this to be 10 millimeters, and then this also set to 10 millimeters. Also, we would like this to be 8 millimeters. And we have our core material. Now let us also complete the coil here. So let me just draw a coil. Now we will do some dimensioning. The coil is located at just 1 millimeter from the edge of the core. And then let's dimension the coil as well. This is going to be 7 millimeters. And we will set this equal to 7 as well. And the width of the coil is set to 12 millimeters. So we have the core, we have the coil. We also have a steel plate. So let's go ahead and do that as well. So we have a steel plate, the length of which is set to 30 millimeters. The width is set to 3 millimeters. And then the steel plate is located at about 7 millimeters from the top of the core. So we have these three things. So I will immediately go to surfaces and I create planar surfaces on this sketch. So what I have here is a core that is going to be made of a ferromagnetic material. I have a coil and I have a top plate. Now imagine these are not really 3D geometries. So imagine that I take this line as the axis and I revolve these three things. And that is really what represents our 3D geometry. Because we are doing a 2D simulation, which is going to be axis symmetric, we are just happy to do these things. Now let's draw the air geometry as well. So again, we take the top plane, we create a sketch, and then we will convert some entities. Let's convert these three lines as well as these three lines. So once we convert some entities, we're going to join them really using some free form. So we know that we can now create a surface because SolidWorks kind of highlights this in a different color. But let's go ahead and do some dimensioning. So I'm going to make this 60 millimeters. And then we also make this 50 millimeters. And also finally dimension this to be equal to 50 millimeters. And then we go back to surfaces and then create a planar surface with the sketch. So right now I have the air, which again will be revolved about this axis. Then we have the core, we have the coil, and we also have the top plate. Now, before we start the simulation, there is just one more thing to do. I want to insert a coordinate system. I'm going to pick this point. For the x-axis, I'm going to select this edge. For the z-axis, I select this edge, and then we just okay. So now this is how I would like to align x and z, and say OK. So I have the surfaces and I have the coordinate system. All I need to do is save this geometry. I'm going to save it as the example 2, axis symmetric. And then now we are ready to go ahead with the EMWorks 2D simulation. So let's go to the EMWorks 2D manager. We create what is called as a study. It's going to be magnetostatic study. I'm going to take the 2D geometry. I'm going to select axis symmetric RG. Select the coordinate system. Say OK, and the study tree is created for us. From the window, the model window, I select the surface that represents the air. Notice that it is automatically selected in my feature tree. So I can go ahead from my favorite material, select air. Next, I zoom in, select copper. From the favorite material, select copper. And last but not the least, I select the remaining two from the feature tree. And then from the favorite material, select steel 1010. So now I have the materials defined. I'm going to go ahead and define the extremities of the model. I'm going to set the magnetic vector potential at the 3 extreme edges to be 0. Now just make sure that you don't select this edge, which is the axis about which the model is going to be revolved. So just make sure that is not selected. The 3 other edges is set to a magnetic vector potential of 0. Then we are going to define the coil. We're going to select solid coil based on surface. Select this particular surface, and then it's a current driven coil, so let's make it 15,000 amp turns. Finally, we want to compute the force acting on the top plate, so we select the top face representing the top plate and request for the force calculation. So now we can create our mesh. What I like to do is in the mesh options, just vary the element growth rate to be 1.1 and then say OK. So notice that we have some nice mesh elements which are created, and now we can go ahead and run the simulation. So you right click on study 1 and select run. Once the simulation is completed, the solver is completed, we can now take a look at the results. Okay, now that the simulation is completed, let us go ahead and take a look at our results. The first result that is of interest to us is to compute or look at the magnetic flux density. So here we can see the areas of the model where we have high magnetic flux density. One other nice way of looking at this is through a vector plot. So right click on the magnetic flux density folder, and from the vector plot select no clipping. Now you can actually see the magnetic flux densities as a vector plot. So in the vector plot options, you can go ahead and reduce the size of the vectors, so that now really gives you how the magnetic flux moves through the core and into the top plate and back here, creates a loop. We can actually select the constant vector size, and that kind of tells you really all the vectors, but really the blue vectors are the ones that have very little flux density. So in case you're looking at how these vectors circulate, this could be a good option. So I'm going to turn it back off so you can look at the magnetic flux density as the vector plot. We can also take a look at the magnetic field intensity. Now you can see the air gaps, high areas of magnetic field intensity. And last but not the least, but I would like to get the flux lines. So I'm going to make them as contour lines, and now this is the magnetic flux lines. You can see the flux lines as it is progressing through the geometry. Now we asked for the force acting on the top plate, so that we can extract from the result table. So let me just shorten the result table to fit inside this screen. So on the force tab, I can now select and look at the force. So I have about 66 newtons of force in the minus z axis. Notice that we created a coordinate system where the z was pointing upwards. So a minus z axis tells you that the force is a force of an attractive force which pulls the plate towards the core. Okay, so just in case you're worried what our coordinate system is, it's not what you see on the bottom left, but it is what we created in SolidWorks. So you have the z, and the force acting was on the minus z axis.